If we take another look at this image from the previous video, you'll notice that each curve's peak wavelength occurs at a different location. And not only that, there are unique temperatures associated with each of these curves. Now, this is not a one-off thing or a rare coincidence. In fact, if you look at any blackbody curve, you'll notice that as the temperature increases, the overall intensity of the light at all wavelengths will also increase, but the peak wavelength decreases. This pattern was first observed by German physicist Wilhelm Wien, who stated that the peak wavelength of a blackbody curve is inversely proportional to its temperature. This concept yielded Wien's law, which states that lambda max, or the peak wavelength of the blackbody, is equal to b over t, where b is Wien's displacement constant having a value of 2,897,772 nanometers times kelvins, and T is the temperature. Now, we're already familiar with nanometers, but the unit used to express temperature measurements in SI units and in astronomy is the Kelvin, named after the Right Honorable Lord Kelvin, who made a lump sum of contributions to various fields of science. Let's use Wien's law in determining the temperatures associated with these blackbody curves. The lambda max of the lowest curve measures in at around 650 nanometers, so we must reorganize the equation for Wien's law to isolate T and solve for the temperature. We'll divide Wien's constant, 2,897,772 nanometer Kelvin, by the lambda max of this lowest blackbody curve, which is 650 nanometers, and after we cancel the nanometers, we get 4,458 Kelvin, which is approximately 4,500 Kelvin. Also, keep in mind, when we use the Kelvin as a unit of temperature, we actually avoid using the word degrees before saying Kelvin. So these temperatures are actually 4,500 Kelvin, or 6,000 Kelvin, or 7,500 Kelvin for the middle and tallest blackbody curves, whose peak wavelengths are about 500 nanometers and 385 nanometers, respectively. Now, Wien's law basically states that a star's temperature increases with decreasing wavelength, which means that a blue star, like Rigel, is much hotter than a red star, like Betelgeuse. Now, Rigel and Betelgeuse are two of the most prominent stars in the constellation Orion, so they make great examples for this concept. Now, let's work through a couple of other examples. Which of these stars has the highest temperature? Take a moment to look through these options and select the letter of the right answer. If you chose C, you're right. Now we're looking for the star that had the lowest peak wavelength value, and that's the star with the lambda max of 320 nanometers. The shorter the wavelength, or the lower the number that represents the wavelength, the higher that star's temperature will be. So now let's see, which of these stars has the lowest temperature? Look through these options and make your selection. If you answered A, you got it. Red stars have extremely long peak wavelengths, so that makes them the coolest in terms of their temperature. Now, just to clarify some terminology, when we say longest peak wavelength, I don't mean a peak that's extremely high. This graph that you're looking at would actually imply a short peak wavelength or a short lambda max, so that's not what we're imagining when we say longest peak wavelength. When we say longest peak wavelength, we mean something more like this. However, nature is never actually this neat and tidy when it comes to stars and their spectra. We actually don't have such smooth curves to look at when we look at the spectra of various stars. Here we have the spectrum of a star that's very much like the sun. So what is the temperature of this star? We can figure this out by finding the lambda max and then calculating the temperature using Wien's law. But what's the lambda max? In order to find it, we have to look at the continuum of the graph. And that happens to be the basic shape of the blackbody curve of the spectrum of the star. To get a better idea of what a continuum is, we basically look at this curve here and imagine it without all of the spiky peaks and dips and its raggedy features. A smooth curve, like the one that's drawn in blue on this star's spectrum, is the continuum of that star's blackbody curve. Identifying this continuum can definitely help us find the peak wavelength, which in this case is about 465 nanometers. So using that value can give us the temperature of the star by dividing Wien's constant by the wavelength, and we get a value of about 6200 Kelvin, which is slightly warmer than our own sun. But what about the temperature of this star? After we identify its continuum, we can read the value for its peak wavelength and find it to be about 780 nanometers. Using Wien's law again, we can divide Wien's constant by 780 and get a temperature of about 3700 Kelvin for this star.